All right, so now what we're going to do is we're going to take a look at the law of sines. And so where we are is section 9.2, which is going to begin on page 551. And this is our law of sines. This is not new to you. You guys did this back in geometry. So anytime you have a triangle, and you want to find values of missing angles or missing sides, we have a number of different things that we can use. And which things we have available to us depends on whether we have a right triangle or not. So when we do have a right triangle, we have things like the Pythagorean theorem available to us, and we have our right triangle trig. We have SOHCAHTOA available to us. The problem is that when we don't have a right triangle, we cannot use SOHCAHTOA or the Pythagorean theorem. The reason that we cannot use SOHCAHTOA is because there's no opposite adjacent and hypotenuse the same way, because there's no hypotenuse in a non-right triangle. So we have to have other tools, and one of those tools is the law of sines. The law of sines is something that you only really use for non-right triangles. It's not that you can't use it for a right triangle, but there's absolutely no need to, because you can just use SOHCAHTOA, which is cleaner and simpler. So if I have a non-right triangle with angles capital A, capital B, capital C, and sides little a opposite from big A, little b opposite from big B, little c opposite from big C, it turns out that the sine of angle A divided by its opposite side is equal to the sine of big B over its opposite side, little b, is equal to the sine of big C over little c. Now, there are three equations built into this double equation here. You're not going to use all three of these things at once. You're either going to use the A's and the B's, or you're going to use the B's and the C's, or you're going to use the A's and the C's. Okay, this is just a convenient way of writing them all at once. The key to law of sines is that in order to use one of these proportions and solve for a missing value, you must know an opposite pair. In other words, you either have to know capital A and little a, or capital B and little b, or capital C and little c. If you do not know an opposite pair, then when you try and set up law of sines and solve, you're going to be missing two variables, and you're not going to be able to solve one equation for two variables at the same time. So that's how you know when you can use law of sines and when you can't. Now notice that I said that this is a non-right triangle. So how do we actually use the sine function in a non-right triangle? And so what's going on here, guys, is that the law of sines is used for non-right triangles. What it does is it actually cuts our triangle into right triangles, and then it uses opposite, adjacent, and hypotenuse, in this case opposite and hypotenuse, from those two right triangles to create this. So it's cutting a non-right triangle into right triangles automatically for us. Okay, so that's how it allows us to use this. So let's take a look at an example here. Now, before I take a look at an example, I want to point out a couple of things to you. Going back to geometry, there were 4 different ways to prove that triangles are congruent. Non-right triangles. And those were side, 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 angle, side, angle, side, angle, and angle, angle, side. These are going to be the two versions that you use law of sines on. These will be the two that you use law of cosines on. Okay, and we'll talk about that in tomorrow's video. So today we're talking about the two that you use law of sines on. Now, there is actually a third one that you use law of sines on, and that is angle, side, side. But you have to be very careful with this one. When you're given this information. Because going back to geometry, remember, that was not one of the 4 that we could use to prove that triangles are congruent. Because angle, side, side information is not enough to guarantee you only one shape of triangle. It turns out that there's the potential, there's not a guarantee, but there's a potential for a second totally differently shaped triangle to come about from that same information without changing anything. And so we'll talk about that in just a moment. I'm going to do an example of the normal ones, the angle side angle or angle angle side for you, and then I'll do one of the angle side side ones for you. And then we'll do law of cosines tomorrow. So let's take a look at our first example. Bear with me one moment here. So what we're going to do is we are going to take a picture that looks like the following. We have a triangle. I'm going to call this A, B, and C, which makes this little a, little b, little c. And you're going to be given some information. So we're going to be given that angle A is 75 degrees. We're going to be given that angle B is 62 degrees. And we're going to be given that little a is 10.2. Notice that what we have here is angle, angle, side. And this is one of the theorems that we can use in geometry to prove that a triangle is congruent, meaning there's only one triangle that has this particular information. And so there's no danger here. So what we're going to do then is we're going to go ahead and solve this triangle. And again, you did this in geometry. What that means is we have 6 things in this triangle. We have the measure of angle A, we have the measure of angle B, we have the measure of angle C. We have the length of side A, the length of side B, the length of side C. There are 6 things that we need to know. We have been given 3 of them. They're always going to give you 3 of these. We've been given this one, we've been given this one, and we've been given this one. Our job is to figure out what this, and this are equal to. Now, the easy one is to find angle C. Because we know 2 of the angles, and we know all 3 angles have to add up to 180, 75 plus 62 gives us 137, and 180 minus 137 leaves us 43 degrees, so therefore this we know is angle C. So we can find that easily. Now, if you're given the angle side angle case, let's say we were given angle C is 43, and angle B is 62, and angle A is 10.2, that's angle side angle, you would also start by finding the third angle by adding them up and subtracting from 180. Remember I mentioned a little while ago that to use law of sines you have to know an opposite pair. Notice we know big A and little a, we can use law of sines here. Okay? If we knew big B and big C and little a, we would not know an opposite pair to begin with, but by finding angle A, by adding these up and subtracting from 180, we would then know our opposite pair. So this really takes care of the angle-angle side or the angle side angle case as well. This is starting out as angle-angle side, but angle side angle would start very similarly. Now what we're going to do is we can either find little b or little c. It's up to us since we know both big B and big C. We have to use the opposite pair that we know, the a's. And so now from law of sines, we know that sine of angle A divided by little a has to equal sine of angle B divided by little b. But we know that angle B is 62 degrees. Notice we have one variable which we can then solve for. So now I'm going to cross multiply and I get B times sine of 75 degrees is equal to 10.2 times sine of 62 degrees. Divide both sides by sine of 75 degrees to get B by itself. And what we end up with then is this. So let me actually just do it this way rather than erasing, for those of you that are taking notes on this. So it's still up there for you. You don't have to rewind necessarily just to get this. This would be our exact answer in terms of sine value, sine functions. Now, we can get this using our calculator. Now, understand, sometimes these will be unit circle angles, in which case you should get this exactly, not using your calculator. If it's 30 degrees or 45 or 60, get this in terms of radicals. Don't use your calculator. But this one doesn't use unit circle values, so we're going to have to get this in terms of, sorry about that, in terms of decimals. So let me pull my calculator up. So now that I have my calculator, let me make sure I'm set to degrees, which I am. 10.2 times sine of 62 degrees divided by sine of 75 degrees is going to give me a value for little b of about 9.3. Unless they tell you otherwise, go ahead and round to the nearest tenth. 9.3, so this is then 9.3. We have one thing left to find, and that's little c. Now, notice that we have big A and little a, we have big B and little b. I need one pair of opposites, so I could use either one of those opposites to help find angle c, or little c. My recommendation, guys, go back to the a's. Why? Because those were the values that were given to us. That way, if we made a mistake finding little b, we still have a chance of getting little c correct. Okay, and I can still at least get partial credit, even if I don't get full credit. If I made a mistake using or finding little b, and then I use little b to find little c, I'm guaranteed to get the wrong answer for little c. Okay, so be careful with that. It's safer to go back and use the a's. So what we're now going to do is we're going to now do sine of a, which is 75 degrees, over 10.2, which is little a, is equal to sine of c, which we found is 43 degrees, over little c. I cross multiply. C times sine of 75 degrees is equal to 10.2 times sine of 43 degrees. And so c is equal to 10.2 sine 43 degrees over sine 75 degrees, which when I go to my calculator, (10.2) times sine of 43 divided by sine of 75 is going to give me a value of about 7.2. I have now solved the triangle. Now, you need to avoid the common mistake. What do people do all the time, even though I warn them not to? Once they get little b and they have little a, they say, oh, well, 9.3 squared plus 10.2 squared has to equal 7.2 squared. No, that is not correct. Why is that not correct? Hopefully you all got the answer to that correct. The reason that that's not correct is this is not a right triangle. You cannot use the Pythagorean theorem on a non-right triangle. That will get you the wrong answer, guaranteed 100% of the time. So this is the idea of solving a triangle. What I'm now going to do is I'm going to talk to you about that danger case. We're going to talk about the angle side-side case, and let me show you what you have to do with that. So here's our angle side-side danger case. This is called the ambiguous case. It's ambiguous because we don't know how many triangles we're going to get. On that last case, we knew we were going to get one triangle. This time, we're not necessarily going to get one triangle. We might get two. Or we could potentially get none. We're not really going to talk about that too much. We'll talk about that on the homework if we run into it. So now what I'm going to do is I'm going to draw a triangle for you. It's going to look like this. This will be our last example for this video. And so we have A, we have B, and we have C. We have little a, little b, little c. And we're going to be given that little c is 8. We're going to be given that little b is 4 times the square root of 2. And we're going to be given that big C is 45 degrees. So, measure of angle A, measure of angle B. B, measure of angle C, little a, little b, little c. We know little c is 8. We know little b is 4 square root of 2. We know that big C is 45 degrees. Our job is to find these three things. Notice that we have angle, side, side information. Notice the angle is not included, not sandwiched between the two sides. So it's not side, angle, side. It's angle, side, side. That does not guarantee us one shape of triangle, and that is our issue here. That's why we couldn't use it in geometry to prove triangles congruent. Now, we're going to start this exactly the same way we did the last one. We know an opposite pair. Now, we can't find the missing angles yet because we don't know two of them so that we can find the third one. But we do know one pair, so we can use law of sines. So we know that sine of C over little c is going to be equal to, and I'm going to find b first again. So let's do sine of angle b, which we don't know, over little b, which we do know. Notice I can now cross multiply, which gives me 8 times sine of angle b is equal to 4 square root of 2 times sine of 45 degrees. Notice this time, guys, we have a unit circle value. And we know that sine of 45 degrees is square root of 2 over 2. So then I get 8 times sine of b is equal to 4 rad 2 times rad 2 gives me 8 divided by 2 is 4. Which then gives me sine of b is equal to 4 over 8, which is 1/2. That makes b equal to inverse sine of 1/2. So 1/2 happens to be a unit circle value, so we don't need our calculator for this. But obviously, if that came out to be something like 3 over 5 or 0.729, we would then punch inverse sine of that value into our calculator and get our answer for b, rounding to 1 decimal place. This one happens to be a unit circle value, and we know that sine is equal to 1/2 at 30 degrees. So we know angle B is 30 degrees. So this was a value that we found, right? Let me make that a little bit nicer. If I know this is 30 and this is 45, those add up to 75. So 180 minus 75 would leave me 105 degrees for angle A. Now, I know my opposite pair that was given to me, sine of 45 divided by 8 is equal to, now I can find little a by using sine of 105 degrees divided by little a. That gives me a sine 45 degrees is equal to 8 sine 105 degrees. I now know that a is equal to 8 sine 105 degrees over sine of 45 degrees. Now, 45 is a unit circle value, but 105 is not. So we're not going to be able to get this as an exact answer. So now we have no choice but to use our calculator for little a. And so 8 times sine of 105 divided by sine of 45 is going to give us an answer of about 10.9. So we found this, and we found this, and we have now solved our triangle. So back that up, rewind, replay it if there was anything that you got lost on. We're not done with this problem, though, guys. This is just the first version of the triangle. We have not yet checked to see if there's a second version. Now again, because this was angle side side and we have the ambiguous case, we need to check for a second triangle. So what I'm going to do now is I'm going to erase these and I'm going to check for the second triangle. I'm actually just going to erase this. Remember when we started this problem, we did not know what this was, we did not know what this was, and we did not know what this was. We only know these through three things. And what we did was we found an angle first. We found angle B. When you are solving the angle side-side case, you're always going to be finding an angle first. What you then do to check for the second triangle and you always do it this way, is you take the angle that you found and you subtract it from 180 degrees. So we do 180 degrees minus our 30 degrees that we got here. That equals 150 degrees. What you now do is you now take that 150 degrees and you add the given angle, the one they gave us. Notice 150 plus 45 is 195 degrees. Can two angles of a triangle add up to 195 degrees? The answer is no. Because it leaves you no degrees left over. You already have too many degrees and you haven't even looked at the third angle yet. So what this tells us is that because this adds up to more than 180 degrees, there is no possibility of a second triangle. Because if there was a second triangle, then angle B, instead of being 30, would be the 150. So what you do is you do 180 minus whatever this first answer is that you got. You take this plus the angle they gave us, the 45 degrees, and you see if it's less than 180. If it's less than 180, then you can find the remaining angle. And then what you would do is you would put or, and or. And you would resolve the triangle using our new answer for angle B, in this case 150, our new answer for angle A, and our new answer for little a. So for example, let's do a what if. What if this, instead of being 45 degrees, now obviously that would change our numbers all through here. But just to give you a what if, let's say this was 15 degrees instead of 45. What would 15, our given angle, plus this 150 give us? Well, that would give us 165 degrees. When we add them together, that's less than 180. So now there would be a second triangle. And so what you would do is you would take this 150 and you would put it here. And so you would put 30 or 150. If this was 150 and this was 15, that adds up to 165. That would make this 15 degrees as well. And so this would be 105 or 15. And then you would use law of sines to figure out what little a is. Now it turns out this would be isosceles, and so we know that this would end up being 8. Because if base angles are congruent, then the opposite sides have to be congruent. But typically, you'd have to go through law of sines again. So what you would do is, for the three things you had to find, you would find a first set, the 105, 30, and 10.9. You would also find a second set, 15, 150, and 8. And so that's how you would do this. Okay? So you're not guaranteed a second triangle, because we saw on this particular one that with this being 45, this came out to be too big. So here there was no second triangle, so we don't have to go through any of that additional work. But if there is a second triangle, all you do is you draw yourself another picture, put in the three things they gave you, put in the new answer that you got for angle B, 180 minus this answer, and then finish the triangle again. And that's the key. So that's our ambiguous case. All right, guys, I will now get you started on the assignment.